A consequence of linear approximations is an idea called differentials. This idea of differentials is an extremely important study for antiderivatives. Let's begin with a definition. Let f be a differentiable function on an interval I containing x. You can think of all the x values here being in the domain of that differentiable function. A small change in the x direction is denoted by dx, and this dx is defined to be the actual change in the x direction. So, dx is equal to delta x. The corresponding actual change, called delta y, is the difference of these two y values. And this is approximately the differential dy, which is a proportion of dx, where that proportion is calculated by the derivative function. Once again, dy is equal to a proportion of dx. The actual change is now approximately this theoretical change called dy. Once again, I'll say that the actual change in the y direction is approximately this theoretical change in the y direction. Note that dy and dx are called differentials. We can illustrate this change or small changes with a geometric picture. Consider a function f of x, and you have its linear approximation right there at the point of tangency, which is x. So there's the linear approximation at the point of tangency, which is x f of x. We can see that delta x and dx are the same. However, dy is measured from the linear approximation, and dy is not the same as delta y. Notice the actual change in function values is right here. The actual change in function values is from this y value to this y value, this y value to this y value. The theoretical change is calculated from the linear approximation. In this particular case, is dy an underestimate or overestimate of delta y? We can clearly see that this is an underestimate. Another way to see that this is an underestimate is locate your linear approximation. Is it below the actual function or above the actual function? In this case, the linear approximation is below the actual function. That will also illustrate an underestimate. You can also remember that dy is a proportion of dx. Remember that this proportion is represented by slope. So if the slope is more than 1, then dy will appear larger or longer than dx. If the slope is less than 1, then dy will appear less than dx. Let's look at this example here. The slope of this tangent line appeared to be less than 1. Since the slope of the tangent line is less than 1, dy, the theoretical change, seems to be less than the actual change. Now, when you study antiderivatives, you don't need to draw this geometric picture over and over again. We simply just use the definition and we look for a differentiable function. Let's look at these examples and let's express a relationship of differentials. The word relationship here just means an equation. For the first example, we can definitely see that y is a function of x. And it's a differentiable function, so we'll go ahead and take the derivative using the quotient rule. Now remember, in the quotient rule, you never need to expand the denominator. Once you calculate this derivative, just use the definition of differentials and write such an equation. Just make sure you write the differential dx high enough so that it could actually represent a quantity in the numerator. Sometimes your independent variable is not always x. Sometimes it could be t. So in the second example here, y is a function of t, and this function is differentiable. Go ahead and use the chain rule. And once you calculate that derivative, simply use the definition for differentials, and we could actually write that relationship. Here are a couple more examples. These are relatively simple. These just require your basic rules of differentiation.